Hey everyone, this is a continuation of momentum section. I'm covering the second part of the theory behind it, and this is just angular momentum, and I'm going to cover the three cases of angular momentum today, or in this video. Okay, so the first case is where the rotation only curves about the center of mass, which is also the center of rotation. So that is represented by the angular momentum equals I bar multiplied by omega, where I bar is the mass moment of inertia of the object, which depends on what kind of object it is, but it's a constant value. Okay, this is simply the motion of a rigid body about its center of mass multiplied by the mass moment of inertia of the body about the center of mass. And it's only applicable to objects that are rotating about a fixed point, which is also at the center of mass. Okay, so the time rate of change, or we'll look at the sum of the moments first. The sum of the moments we know to be about the center of mass to be the time rate of change of angular momentum. But since our I bar value is a constant, we then end up getting I bar alpha. Okay, we can also see that since the angular momentum about the center of mass is comparable to linear momentum, it follows that differences in angular momentum may be found at instance by separating it into time-dependent components like so. Move that up. Like so. Okay, and that is because when a moment is applied, the angular momentum changes, or the angular momentum about the center of mass changes. So our initial angular momentum and an applied moment for a period of time and gives us a resultant angular momentum, which is this here. Okay, that's the first case. In the second case, we also deal with a displacement from the origin. Okay, what I'll do is I'll draw a diagram here so that you understand what I'm talking about. If we have a bar like this, or even a ring, it rotates about this only, and there's no linear component of motion, or it could rotates about this. So omega's about that, omega's about this, and they both have, so we'll say this is a ring and this is a rod. They both have their own unique mass moments of inertia based on their geometries, and that's covered in tables to a greater extent. For a rod, it's 1 on 12 ml squared, and I know that off the top of my head, but I suggest you learn it from, or you use it. You use the whatever's supplied in your exam or quiz or whatever, because you're not going to remember it, because there's a lot of things to remember apart from this. And for a ring, it's mr squared. But they may vary depending on the geometry that you're given. Okay, so the next thing with case 2 case 2, we're looking about angular momentum about an origin point or an origin position. And in case 2, we have the angular momentum about position or origin is equal to the mass moment of inertia multiplied by the angular velocity. So that's the rotational component about the body, plus the linear momentum multiplied by its displacement. But that linear momentum is of the center of mass of the body. So m v bar, where v bar is the velocity at the center of mass, and d is the perpendicular distance from the point O to the center of mass. So if we have a point O here, so that O, and we have some random rigid body like this, and this is our center of mass, G here, and the body is in linear motion like this, so m v bar like this, and it's also rotating about this point, this center of mass here, so it's rotating counterclockwise here at an angular velocity of omega, which we have not determined, and there's also a perpendicular distance here. So we can look at our angular velocity in terms of, or angular momentum in terms of the geometry of this shape, which we can get by integration using the formula for centroids to find the center of mass, which is just integral of rho squared dm, where rho is the position from the center of mass to any position on the outside of the rigid body. The next thing that we consider is the third case, and that's where there is only rotation about a fixed point, which is not the center of mass. So the third case, I should probably say first that we're going off G equals mv, or G about the center, G at the center of mass is mv, and that is represented by this bar on the top. And we could also separate the components of motion like we did in case 1, like so, into time-dependent components. h0, or h about the origin 1 plus t1, t2 of some moments about point O dt equal to, this is getting a bit repetitive, but this is how it works. And this is our resultant angular momentum. And that's because of, well, we found the difference between T2 and T1. Oh, sorry, T2 minus T1, and then added the component, which will, the sum of the moments multiplied by the time at T1 is equivalent to this term here. And that's how we get this term in here, but with integration we get the difference, so that's how we end up with our final angular momentum. Alright, we'll look at case 3 now. In case 3, is with angular momentum of a body, like so, fixed here, rotating counterclockwise and the center of mass is here. So that's our G, that's our O. So as we know from our third case 1, this component, or the angular momentum just with the rotation about the center, is I bar omega, and our linear momentum here, which would be instantaneous, is our mv. Now v can be represented as r omega if we're converting from linear to angular momentum, or sorry, linear to angular velocity. So the formula we end up getting is h naught equals I bar omega plus m r bar squared omega. And the r bar is the distance in here from the origin to the center of mass. Now it's important to note that our linear velocity, v bar at the center of mass, is equivalent to r bar omega, as we've learnt in kinematics, or two-dimensional kinematics. So this in here is equivalent to having mvr, which is roughly the same as mvd. It's just the only difference is it's a radial length as opposed to a perpendicular distance. Alright, so we know that r bar is the vector from the fixed length, or from the fixed origin to the center of mass, and since this is equivalent to a perpendicular distance from the origin to the center of mass, the linear momentum considered at an instant is mr bar squared omega, as we've said before. Now, this looks very similar to the parallel axis theorem, because it is, and if we want to simplify this question in such a way, we can consider first our moments of inertia and make them in terms of a moment of inertia about the point O. And to do that, we use the parallel axis theorem, which is our I bar, which would be 1/3 ml squared, because it's about a point and not about the center. And we just add our mr bar squared here, because omega is a common term in both of the components of angular momentum about the point. So we can then go, if we look up here, I bar plus mr squared both have omega as a factor. So we can then just say that h naught is equal to I naught, or sorry, HO is equal to IO omega, where IO is the angular, the mass moment of inertia about the point O. Alright, that's all that's necessary for the impulse momentum section. There'll be examples at the end of this. Thanks for watching.